Howdy, this is Browdy. So I'm going to do my best to keep this one nice and short, but this is the first of two discussions for Unit 5. So this is discussion 5.1, and really this is going to be the beginning of bonding. And so today we cover just kind of the basics of bonding, the reason behind bonding, and the types of bonding. So let's get started. The first thing that I want to actually talk about is dot structures. And so there's a little chart here that goes through, it's kind of like a condensed version of the periodic table. So you'll notice we have groups 1A and 2A, and then we skip to 3A. So we cut out all the transition metals, and we're only showing the first four periods. So 5, 6, and 7 aren't there, but it's enough to get the point across. So the first thing I want to show you, or I guess I'll start with this. Hopefully we remember what dot structures are. A dot structure just has the chemical symbol of an element. So for example, hydrogen is H. And then it shows how many valence electrons that an atom of that element has. So for hydrogen, it has one electron, right? Its atomic number is 1, which means it has one proton and one electron. So here we'd show hydrogen with a single electron. Now I'm going to skip over to helium because that's element 2. Now helium, hopefully if you can remember back to Unit 4 in our electron configurations and our orbitals, helium is 2 electrons, and that second electron is the second electron in the 1s orbital, which fills up that first orbital and that first energy level. So unlike a lot of the other elements that have 2 valence electrons, helium, we're actually going to draw like this, where it's got 2 electrons on one side, because it can only hold 2 electrons, so we consider that orbital to be full. Now I'll come to that in a little bit. Now, if we look at lithium, lithium is 3 electrons, but only 1 valence electron. So lithium has 1s2, 2s, 1. So it only has 1 electron in that second energy level, or that valence shell, as it might be called, which is the outermost energy level. And so lithium has 1 valence electron. Now hopefully you remember that if it's in group 1A, it has 1 valence electron, because hydrogen is 1s1, lithium is 2s1, sodium is 3s1, and potassium is 4s1. I apologize if I'm a little congested here. We keep going and we get the same thing. Beryllium has 4 electrons, but it's 1s2, 2s2. So 2 valence electrons, and it's in group 2A. So we put each of those electrons on different sides, unlike helium, because we can keep filling these up, right? It can hold 6 more. The same thing applies to magnesium, to calcium. Now we get into 3A. So this is 3 valence electrons, because it's 1s2, 2s2, 2p1. So between s2 and p1, that's 3 electrons in that second energy level. And so we'd put 1 on each side, or of the 3, each one would be on its own side, and we'd see that for boron, aluminum, gallium, and so on. The trend continues into 4A, where each one is still on its own side. Now 5A, we start to double up, finally, because there's 4 sides, and so once we filled up all 4 with 1, then we can double up. So we see that for 5A, 6A, 7A, and 8A. Now the reason that helium is over here in 8A is because for helium, that's completely filled up with electrons. For neon, argon, and krypton, those are also completely filled up with electrons, and we call those the noble gases. So we put helium in group 8A because it behaves like these as opposed to like these, and that's because its orbital, or its valence shell, is full. So now that we've covered that, we can start talking about ionic bonding. So valence electrons are going to be really important for the rest of, really, the class. So what ionic bonding is it's the first kind of bonding we'll talk about. And ionic bonding is when charged atoms are formed by gaining or losing electrons. Now, a charged atom is what we call an ion. So ionic bonding, or ionization energy, if you remember that from 4.3. 2 kinds of ions can be formed: positive or negative ions. So Every atom on the periodic table, or every element as it stands, is neutral, where there's an even number of protons and electrons, right? Atomic number is the number of protons, and the number of electrons matches that. But if electrons are gained or lost, you can get an ion. So a cation is a positive ion, and that happens when electrons are lost. So these tend to be metals. So metals often will lose electrons, and when they lose electrons, they now have more positive charge than negative charge. And if there's more positive than negative, right, more protons than electrons, the charge is going to be positive because the positive outweighs the negative. The opposite is true for anions. They're negative, they're formed by gaining electrons, and they tend to be nonmetals. So the metals, right, the left side of the periodic table, tend to form positive cations, and the nonmetals, the right side of the table, tend to form negative anions. Now, we're going to see a little bit more closely how that happens here. If we start with sodium, sodium has one valence electron. Its dot structure looks like this. And then the question stands, is it going to gain or lose an electron, and how many? So sodium has one. Now here's where we need to explain the main idea of bonding, which is right here. Atoms bond together so that they can have 8 valence electrons. So in general, atoms that have 8 valence electrons are stable because they have the electron configuration of a noble gas. So if you remember, in the past I've said that noble gases are called noble gases because they're too noble to interact with anything else. So they don't interact, they don't bond. And really, they don't need to because they have a full valence shell of electrons. Their outermost energy level is completely filled with electrons, so they have nothing left to acquire. So here, sodium has one valence electron, and it wants to get the electron configuration of a noble gas. And it has two options. It could, if it's got one, it could gain 7 to get the noble gas configuration of argon, or it could lose 1 electron, right? It's got 11 currently, and if it lost, or it's got 11 total electrons. So if it lost its 1 valence electron, it could have the noble gas configuration of neon, right? Because if it loses its 1 electron in the outermost energy level, then there's none occupying it, so then its valence shell becomes the second energy level, where it would be full. And so it's much easier for it, right? There's fewer steps to just lose 1 than gaining 7. It's the shortest pathway. So sodium is going to lose 1 electron and then have a charge of plus 1 because there's now 1 more proton than there is electrons. And when it's a plus or minus 1, we don't write the 1, we just leave it as plus or minus. Now this trend continues with magnesium. Magnesium has 2 valence electrons. Now is it going to gain 6 to get to argon or lose 2? Well, it's going to lose 2, right? That's the shortest pathway. And so if it now has 2 more protons than electrons, it has a charge of plus 2. Aluminum, same idea. It could gain 5 or it could lose 3. It will lose 3 to get the noble gas configuration of neon, and it'll have a charge of plus 3. Now, group 4A, we don't really see anything happen because they have 4. It could gain 4 or lose 4, and because of that, it doesn't lean one way or the other, so we don't really see these participate in ionic bonding. Now, 5A, nitrogen, phosphorus, and aspartame, right? These could go a number of different ways. It could go down, it could lose electrons like everything else, but it could lose 5 or it could gain 3. So here it's going to be easier to gain 3. And so in this case, nitrogen is going to gain 3 and have a charge of negative 3 because it's gained 3 electrons. There's 3 more electrons than there are protons. Oxygen is going to gain 2 rather than losing 6, and fluorine is going to gain 1 rather than losing 7. And the charges will be as follows. So that's entirely based on how many valence electrons they have. And they're trying to get to 8, either by gaining or losing. Now lithium, for example, is going to lose 1, and rather than having 8, it'll have 2, but that's because that's helium's noble gas configuration, so that's okay. And that's the basics of forming an ion. Oh, sorry, I went a little too far. I'll be a little bit more careful this time. Okay, now I'm going to zoom in on this if I can. I can. Okay. So what we see going on here is this is asking how different things bond in the ionic sense. So how does sodium bond with chlorine, right? That's NaCl, which is our good old friend, table salt. So sodium and chlorine will form sodium chloride. But how does that happen? Sodium has 1 valence electron and chlorine has 7. Sodium wants to lose 1 and chlorine wants to gain 1. Now we'll explain why this happens in 5.2, but essentially chlorine is pulling on electrons more tightly, and so chlorine needs that 1, and so the 1 electron from sodium gets given to chlorine, which needs 1. Sodium then has noble gas configuration. Chlorine then has noble gas configuration. But this has a charge of +1, and this has a charge of -1. And that's it. Ionic bonding doesn't have a physical connection like you might be used to seeing, where we draw a line between atoms. That doesn't happen in ionic bonding. This is a ratio. So in a mixture of sodium and chlorine, or with a sample of sodium and a sample of chlorine, when you combine those, they will arrange themselves such that there's 1 sodium for every 1 chlorine. For magnesium and oxygen, the same thing happens. Magnesium, and I'm sorry for this little symbol here, magnesium has 2 electrons and oxygen has 6. This wants to lose 2, this wants to gain 2. Both get donated, and then we get magnesium +2 and oxygen -2. Excuse me. Aluminum has 3, nitrogen has 5, so this wants to lose 3, this wants to gain 3. So we get aluminum with a charge of +3 and nitrogen with a charge of -3. And in each of those cases, we see ionic bonding. Now what we could see, and I don't have this on here, I talked about this in class with the worksheet, but I wanted to include it in the video. What if we had magnesium and chlorine? Because chlorine needs 1, but magnesium wants to get rid of 2. In that case, since chlorine forms a charge of -1 and magnesium forms a charge of +2, we would actually see 1 magnesium bonding with 2 chlorines. So there would be 2 Cl- atoms to total a charge of 2-, right? Because 2 -1s would give us -2. Magnesium would be +2, so there'd be MgCl2, because again, we want to even out that ratio. And that's ionic bonding. Now I'm going to see if I can go down. Okay, I'm going to zoom out a little bit more, and we're going to go back to the top. So that's ionic bonding. And again, I apologize for sounding a little bit congested, but that's ionic bonding, where electrons are donated and received, or gained or lost. Now in covalent bonding, the same idea applies, that atoms want to get their 8 valence electrons, or in the case of hydrogen and helium, they want to get 2. Now ionic bonding was when electrons were gained or lost, and that also happened between a metal and a non-metal. Because remember, the metals want to lose and the non-metals want to gain, so that works out. Covalent bonding is a little different. This happens between 2 non-metals, both of which want to gain. And since neither is going to donate, what happens is that electrons are shared between the 2 atoms. And so still in most cases we want to have 8 valence electrons, and we call that the octet rule. The major exception is hydrogen, which wants 2 electrons to fill up that 1s orbital, and we call that the duet rule. We don't see that happening with helium because helium already has its 2 electrons, so it has nothing to worry about. Now, the way this would look is, remember, each hydrogen has one valence electron. So if you're going to form a bond between two hydrogens, it would look like this, where they get close enough together that those electrons are actually overlapping between those two orbitals. And so they can be considered shared. And so then if you were to cover up this hydrogen, this one has two valence electrons. If you cover up this hydrogen, this one has two valence electrons. None were donated or lost or gained, but each hydrogen just got close enough to one another that the one electron that they each have is within both orbitals and is shared. So for two chlorine atoms, the idea is the same. This one has 7 valence electrons, and this one has 7 valence electrons. They each need to get one more. If they get close enough together, this lone electron and this lone electron can be shared. So these doubled up electrons don't really get messed with. We call those lone pairs, but these are paired up electrons, so we don't mess with those. But these individual unpaired electrons basically are up for grabs. And so what we would do is we would draw it like this, or which really is this, where each chlorine still has 1, 2, 3, 4, 5, 6, 7, 8. Same thing here. We just shared these two electrons. We can represent that with this single line, and we call that a single covalent bond. With hydrogen, the same thing happens. Or sorry, not hydrogen, with water. There's H2O. This hydrogen is 1. This hydrogen has 1. Oxygen is in 6A, and it has 6 valence electrons. So each hydrogen needs to gain an electron somehow, or it needs to form a bond. This oxygen is 2 lone electrons or unpaired electrons that it can do that with. So oxygen can form 2 bonds, whereas hydrogen can only form 1. But there's 2 hydrogens. So it pairs up like this. The oxygen forms 2 bonds with the 2 hydrogens. So that looks like this. This hydrogen has 1, 2 electrons. Same thing here. And this oxygen has 1, 2, 3, 4, 5, 6, 7, 8, because each of these lines counts as 2 electrons. It's a pair of electrons that's being shared, and we draw that as a single bond. Now, covalent bonding can also share more than just 2 electrons. So in carbon dioxide, for example, oxygen has 6, and there's 2 of them. Carbon has 4 valence electrons, and there's just 1. Carbon can form 4 bonds because it has 4 unpaired electrons, and oxygen can each form 2. So if we draw a bond here and a bond here, just 2 single bonds, carbon would have 2 left and oxygen would each have 1 left. So we do it again, and we end up with double bonds. Each one represents 2 electrons. So here we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8 for each oxygen. And carbon has 1, 2, 3, 4, 5, 6, 7, 8. And so if we were to draw it as a dot structure, it would look like this. So a double bond represents 4 electrons being shared. So these got even closer, so more electrons could be shared. And we call that a double bond. Those are stronger than single bonds, and they're a little bit closer together than single bonds as well. You can also have triple bonds. So if you look at 2 nitrogens, right? Nitrogen has 1 lone pair and 3 unpaired electrons. So it can form 3 bonds each. So if you form 1, there's still 2 unpaired electrons. If you form a double bond, there's still 1 unpaired electron. So we form a triple bond, which is 6 shared electrons. And it looks like this. And that's as many bonds as can be formed in covalent bonding. But now each nitrogen is happy. 1, 2, 3, 4, 5, 6, 7, 8, or 7, 8. And that's covalent bonding. That's the basics of it. I'm doing my best to keep this under 20 minutes. And that's really all the basics. There's ionic and covalent bonding. Ionic is when electrons are donated or gained, and that happens between a metal and a nonmetal. And there's no physical connection. It's a ratio of positive and negative ions. In covalent bonding, this forms molecules or molecular structures. And that's because there are connections between 2 nonmetals where electrons are shared. And there can be single bonds double bonds, or even triple bonds. And there's no donating or gaining or losing of electrons, just sharing of valence electrons. Covalent means together valence. So you're sharing valence electrons together between multiple atoms. So for now, that's all I've got. We'll talk a little bit more about these concepts in 5.2, but for now, I hope this is helpful. If you have a question, you know how to get a hold of me, and I'll see you next time.